No? Gee, I guess we'll have to do some math then. All right, I'm going to start out with my notes in the Word document, but I'll then shift over to those PowerPoint slides, again, because they have everything in the order of the book. My notes are in the order. I'm somewhat biased about this, but I think this is one of the most important courses you're going to take this year. And not just because it's math. Yeah, I do like math. I agree. But it's a very applicable math that you're going to use out there in the real world. And you're using it already, you just might not know it. A lot of you are going to commission. You're going to be officers, you're going to be managers, you're going to be people making decisions. The real value in this 105, 106 sequence is how do I make rational decisions with imperfect information? The real world out there is kind of messy, isn't it? How do I know the right thing to do? And when it comes down to it, that's what statistics is all about, is guiding us in making these decisions. How to make sense out of the real world. In fact, my personal goal that I like to mention to people, you'll hear me repeat this a few times. I want you to become an educated consumer of quantitative information. Another way I sometimes say is I want you to be informed skeptics. Now, being informed is important. Don't just be a skeptic. I'm not looking for people here to believe the moon landing never happened, it was staged. Informed skeptics, meaning I have the ability to look at this information, making a judgment on my own and see if I'm going to believe it or not. I'm going to be able to poke holes in it. I'm going to be able to ask piercing questions to the people who are giving me this information so that I can assess, do they know what they're talking about? Did they do it the right way? Because if you're going to be a decision maker, the quality of the data, the quality of that information is going to be key, isn't it? And let's face it, we're bombarded all the time in our society now with quantitative information. And numbers have this cachet, you know, gee, if it's a number, it's precise, it's accurate, right? Well, nonsense. It's just a number, and it's as good as all of the techniques that were used to create that number. The first couple of weeks won't feel perhaps a lot like a math course. It's going to be a lot of definitions and kind of conceptual stuff. Don't worry, we'll get to the math. But in some sense, it might be the most important part of it because we want you to start thinking statistically, thinking about, reasoning about uncertainty. And one of the few times I'm going to do a YouTube video in this, not the only time, but actually there are a few times. Let's get an example here. Oh, I need the volume here. Come on. Well, let me go back to this again. We're not going to get the... See that? Catch the words? You're missing the effect of the music. All right, over 100,000 people die a year from inactivity. Most have only 7 from extreme skiing. Let's suppose for now those numbers are accurate. They're facts. Right? We can't argue with the numbers, but we can discuss what do the numbers mean. Anybody here an extreme skier? Anybody here a couch potato? You're going to have to answer that. What can you conclude from those numbers? Hundreds of thousands of people died because of inactivity. They're watching too much TV. Only 7 died because of extreme skiing. Should we write our congressman? What would you tell him or her? Yes? Lasky?
Well, yeah, there's a lot more inactive people than there are extreme skiers.
Yeah.
And that's one of the reasons why there's more deaths each year from inactivity.
So, true story. What's kind of the math behind that? What kind of mistake is being made when these numbers are being presented to you?
We're not looking at the percentages of each. If you look at the percentage of extreme skiers and the percentage of extreme skiers that die, and the percentage of couch potatoes, like the number of couch potatoes that die, and the percentages, you might not end up the same.
Exactly. And this kind of sleight of hand, statistical sleight of hand, is pretty common out there. And there are times when it makes sense to compare raw numbers, counts of. Right? And you were presented counts of fatalities in 2 different categories. Sometimes that makes sense to do that. You've got to be careful, though, with the populations, the term we're going to get to in a minute, are very different in those categories. Then you shouldn't be examining counts, you should be examining percentages. Example of statistics, they're correct. There's no lies there. But how do you interpret it? How do you use it? Kind of a silly or a fun one. Yeah, I'll just do one other. Fastest growing car brand in America. I've heard several claims like that by manufacturers, cars or something else. The fastest growing in America. What do you think about that? Go buy one? What could be going on? Be an informed skeptic here. Let's assume it's a true statement. Factually, it's true. They're not lying. Could it be misleading? Now, you've had enough time to digest dinner. I'm sure fine food at Crozet is easily digestible, right? I said, Dylan? Okay, good, Dylan.
Well, it depends on the time period you're looking at for the growth that happened. So if like they had a surge of cars sold in like a week versus like some other company had it in like a year, I mean, they could say that for that 5 minutes they were the fastest growing car brand. Kind of misleading because the time period wasn't really as long.
All right, good point. We don't know if there's a uniform period. Maybe I gave a great sale, 50% off, and I loaded a lot of these clunkers. All right? It's a possibility. Yes?
You could already be a larger car brand, therefore your growth might be slower than if you were a smaller car brand just starting up and you could grow more rapidly.
Yeah, that's what occurred to me. Who's going to grow the fastest? GM or Tesla? Why? Well, they're so tiny now. How hard is it for them to double? I don't know, they sold 5,000 cars? I'm not sure. If they sell 5,000 more, then they've doubled. They've grown 100%. Is it easy for GM to grow 100%? No. All right, so it's not a lie, but is it the information you're really going to make use of? What are you going to do with that? These and a lot more other examples are what I'm going to put in front of you in the next couple lectures. I want you to be educated consumers of quantitative information. Informed skeptics, as it were. Actually, we have time. Let's do one other one. This is, in future lectures, I'm going to give you some examples from news programs and out there in the blog sphere of people making statements with statistics. Here's a conversation that was on one of those Talking Heads program. Someone from Canada said, gee, have you noticed that the life expectancy in Canada under our socialized health system is higher than in the US? That's a fact, that's probably correct. We could check it though. But the person who responded to that said, oh yeah, that's because we have 10 times as many people in the United States. So we have 10 times as many heart attacks, 10 times as many accidents, 10 times as many shootings. That doesn't make any sense. What do you think? Go on, someone in the third row there. You're quiet. Yes. You. I can't see your name.
Russell.
Russell. Okay, Russell. Does the commentator have a good point? Yeah, we're a lot bigger country. Sure, we're going to have a higher death rate.
It's just like the car situation. It's harder for us to double than it is for a smaller population.
Well, if our I just said death rate, it's life expectancy. Any change in our life expectancy would involve a lot more people. But what about his comment? There's another angle to this. Yes, sure.
They're not related. Just because we have 10 times as many people doesn't mean there are many more accidents, crimes, or anything else.
Okay, that's one potential flaw, isn't it? That's good. I hadn't thought of that. All right, we are 10 times as big, but does it mean we have 10 times as many crimes? I don't know, maybe we have 20 times as many. What else is at the kernel here? Yes?
Well, life expectancy is working with averages. And if you're working with averages, it doesn't, like, just because you have a larger amount of pool, if your average is lower, then it's going to be lower, you know?
Yeah, you got it bang on. Basically, this may be true, these things, but so what? I'm looking at a life expectancy, which is a kind of an average over the entire population, right? And just because my population A is 10 times as big as population B, just because America has 10 times as many people, that by itself doesn't mean that our life expectancy should be lower, higher, whatever. Right? Correct, factually correct numbers, trying to lead you to a conclusion that really doesn't make any sense. All right, you're able to sniff those out. Let's get started now. I'm going to switch to for the last 5 minutes here, to the PowerPoints, because they have the correct order of information. As I warned you, the first week probably is not going to feel like a math course because it's mostly a lot of definitions and concepts. Don't underrate the importance of knowing these because everything else is built on it. We do that a lot in math. We fool you. We start out with just simple little ideas and concepts, and then before you know it, we're just putting rockets on the moon. The first distinction to make is population versus a sample. You need to know where your statistics, where your numbers come from. The population, now it all depends on the context of the problem. If I wanted to study the weight of at VMI, then what would my population be? Population is all 1,500 plus of you, right? If I wanted to study the weight of adults over the age of 21 in the United States, what's the population? Well, it's 200, 300 million, something. It's a lot of people. It's everyone that meets those criteria. Well, here's the rub, and this is really why we have statistics. I want to know something about a population, but it's impractical, impossible, or too expensive to find out that information. Think about the recent election and the polling. There's a lot of people on any given day who wanted to know, how is America going to vote? What's the population? All eligible voters, hundreds of millions of people. Is it feasible? Possible? to, in any given day, know what that population value is, the percent they're going to vote for one candidate or another? Could you find that out? Not practically, right? You can't do that. What do we do? Well, if I don't know the true, say, P, the percent are going to vote for Obama, I take a sample and I calculate something that I hope is close to that number. I'm giving you a little bit of a foreshadowing of some terminology. In this case, we call it P hat. Don't worry about that yet. We'll have a long list of symbols. But they point out the distinction between a number that is derived from the population and a statistic that is derived from a sample. I hope that by studying this, we know something about this. Seems kind of obvious and trivial, doesn't it? But that, in a nutshell, is what statistics is all about. So that's what a statistic is. It's some kind of a, usually a computational value that's derived from a sample. And a distinction from a sample would be a census, and that's everybody in the population. Those are expensive, very difficult to do, and you really can't do those very often. In the United States, we try to do a census every 10 years, don't we? But do you think we count every person in the United States every 10 years? No. So in an example, going back to the poll, any poll you see, you should be thinking, when you're looking at the study, what is their population? Who are they talking about? Is it all adults? Is it all adult males? Is it all Republicans? Is it all this? Is it all that? Who are they studying? What was their sample? And in the next lecture, we'll be talking a lot about ways to evaluate if it was a good sample. But we'll just take a minute here. Just right now, off the top of your head, what do you think would be some criteria for a good sample?
A melting pot. A melting pot.
Okay. Now, what's a melting pot?
Like same amount as males as females, about the same age, all spread out.
All right. So I've got to have a representation of a broad representation, don't I? Okay.
I was going to say everyone needs to have the chance to ask the question, like do that like completely randomly.
Oh, good. Yeah. If I'm on a survey, I could ask my 5 friends. I could go out in the corner and ask the first 5 people that walk by. Or I could go through a phone book and randomly pick 5 telephone numbers. Right? Talk more about these techniques. That's good. That's very good. What else about a sample? You, as an educated consumer of quantitative information, what else would you want to know about a sample, do you think? What would make a sample more reliable? What types of things? We talked about randomness. It's got to be representative. Yes?
How many are in the sample?
Exactly. And think if I was studying the Corps cadets and wanted to know the mean weight, now these 3 cadets right here. Is that representative?
It's not accurate.
Probably not. I hope none of you are offended that way. Probably not. And in summer school, I had 2 linemen from the football team. I always picked on them for examples as outliers. He weighed 330 pounds. If that was my random sample, that's not very representative. But taking a larger sample should give me a better estimate. Now, the really interesting mathematical question that we'll start to answer in this course, the next one, is how much does it buy you? Right? I can ask 10 people, I can ask 100, 1,000, 10,000. All right, that's a good breaking point for today. That's your assignment. Make sure you get those done. And then Friday, we're going to go very quickly through chapters 1.1 through 1.4. So look at those notes.